Okay, now recording. And try to share the screen as usual. Okay, so on the schedule, we are here. So 4.2 for today on the mean value theorem. I will finish that today, and I'll probably get started on 4.3. Okay, so we're only on schedule to do 4.3 this week. I think I should be able to do that without a problem. Maybe even start some at 4.4. Okay, quiz on Friday. I'm going to go ahead and say the quiz is going to be on finding the maximum and minimum on a closed interval. So I can get more specific with that. So quiz on Friday will be stuff like 281, that box, closed interval method. Okay, so I'll ask you a question on that on Friday's quiz. Okay, so find the function value at the critical numbers and at the endpoints. And then step 3, the largest of those y coordinates is the absolute max, smallest is the absolute min. Okay, and if you want problems that are like that, right, that was the set from section 1 from 47 through 61, right? Find absolute max and min on a closed interval. So the quiz will be something like 47 through 61 on page 284, okay? So again, for sure, you have to plug in 2 numbers, the 2 endpoints, right? So you have to plug in the beginning and the ending, and then any critical values. Okay, so that'll be the quiz on Friday. All right, so let's get back to the mean value theorem where we were. So last time I did all of Rowe's theorem, and today we'll do mean value theorem. And then hopefully if time permits, which I think it will, get started on chapter 3. And just to let you know where we're headed, yeah, I should tell you, there's going to be a lot of graphing from here on out. 4.3 is pretty much all graphing. 4.5 is pretty much all graphing. So a lot of graphing from here on out. Okay. All right. And by the way, I made a mistake. We're not scheduled to do any 4.6. Okay. On the homework though, or sorry, on the calendar, I included a 4.6, but we don't have to do it. Okay, which means I very likely will push things up. Okay, which further means there's a greater chance that we will have the exam on Friday the 23rd. Okay, so again, I made a mistake. There is no 4.6. So we go from 4.5 to 4.7. Okay, so 4.3 is pretty much all graphing. 4.5 is pretty much graphing. 4.7 is word problems, applied max and min. And 4.8 is something else. Okay, but we'll see how it goes. All right, so back to the mean value theorem. Okay, quick review of Rowe's theorem, page 287. Rowe's theorem, if f is continuous on a closed interval from a to b, differentiable on an open interval from a to b, and f of a equals f of b, the beginning and ending points are at the same height. Okay, then somewhere between a and b, the derivative is 0. Okay, for the mean value theorem, you don't have number 3. You just have number 1 and number 2. So page 288. Again, you're welcome to put this on your next cheat sheet if you wish. Okay. 1, f is continuous on a closed interval a to b. 2, f is differentiable on an open interval a to b. That's just like Rowe's theorem, but there's no number 3. So there's no requirement that the 2 endpoints are the same height. It might look like that, it might look like that, or whatever. Okay. So if they're not the same height, like this, there's a slope joining the 2 endpoints, right? Mean value theorem says somewhere between a and b, that slope is attained. Okay, here's the slope of the line joining the 2 endpoints. F of b minus f of a divided by b minus a. You can put that in your cheat sheet. That's basically y2 minus y1 divided by x2 minus x1, right? Find the slope. Somewhere we get that slope. So again, yesterday I said, that slope looks like it's maybe, I don't know, -0.5. Somewhere the slope is -0.5. Here, notice the 2 endpoints are not the same height. So maybe the slope is 1/3. Somewhere the slope is 1/3. Here it looks like there's 2 such points. Okay. And again, the mean value theorem is really Rowe's theorem on its side. If I tilt the book like this, okay, ignore the fact that I'm tilting the book. If you kind of cover this up and cover this and say, oh yeah, there it is. Same height, slope is 0. Same thing here. Here, if I tilt the book so it looks like this, so if you ignore all the words and the fact that the book is tilted, only look at that and that, you say, oh yeah, slope is 0. So somewhere slope is 0, there and there. Okay, so that's the mean value theorem. The slope of the line joining the two endpoints is obtained somewhere between A and B, provided you have continuous on a closed interval, differentiable on an open interval. Okay, we won't prove it. The proof of the mean value theorem uses Rowe's theorem, as you might guess. The text goes over a derivation of it. You can look at it or not. Okay, so here we go. All right, so problem 3. Okay, I'm not sure how focused this is, but I can't lift up the book here and show you stuff at the same time. All right, so here's a function. Does it look like it's continuous everywhere from 0 to, I guess it's 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. Yes, continuous. Differentiable? Yes. Okay. How do I know it's differentiable? I can take a tangent line anywhere, right? Everywhere I can take a tangent line. This is a safe roller coaster, right? Anywhere, I don't mind being on this ride, right? I don't want to be on a ride that looks like that. You show me this at an amusement park, I'm not getting on it. I don't think you are either. It doesn't look right. Okay, it's got to go like so. All right, so A, functions. So functions continuous on closed 0, 8, differentiable on open 0, 8. So that's that. All right, so estimate the values of C that satisfy the conclusion of the mean value theorem on the interval from 0 to 8. Okay, so again, this is one of those where I have to have you write it down because I can't really write here. So these two are not the same height. Find the slope. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. So the slope is 3/8. All right, I will go ahead and connect them. Somehow my pen got a little bit lighter at the end. So how do I do it? I try to keep that same slope, move it up or down until I get a tangent to the curve. So maybe right there. Whoops, somebody was supposed to knock my hand. So right there. So where's there? I would say 2. So C equals 2. For part B, put C is equal to 2. And maybe there's one down here. Maybe somewhere right here. And just because I want a nice number, how about, where's this? Maybe 7. Okay, so again, you want to keep that slope of 3/8. Move it up like that. So right here, so where's here? 2. Come down. Looks like I have another one here. So where's here? 7. Okay, so the answer to B again is C is equal to 2 and C is equal to 7. All right, then part C, same thing, only from 2 to 6. So from 2 to 6, 3, 4, 5, 6. So the rest of the graph doesn't exist. Only look at this part. Okay, from 2 to 6. Again, let me go ahead and try to graph that from 2 to 6. Okay, that's going to be over 4 and down 2. Just so we can write it, it's 1, 2, 3, 4 over, 2 down. So that's -2 over 4 or -1/2 slope. Okay, so somewhere between 2 and 6, the slope is -0.5. Okay, and eyeballing it, maybe it looks like somewhere over here. Maybe right there. So where's here? I would say it's 4. Okay, so you keep that slope and you basically just move up and down until you get a tangent to the curve. So again, the answer to part C is 4. C is equal to 4. All right, so that's the idea behind that one. And let me raise it up so you can see it a little bit better. All right, then the rest of the mean value theorem problems, similar to what we did yesterday with Rowe's theorem. Okay, so it looks like we have, let's see, 5, 7, 9, those were Rowe's theorem. So mean value theorem 11 and 13. Verify the function satisfies the hypotheses of the mean value theorem on a given interval, then find all numbers C that satisfy the conclusion of mean value theorem. Okay, so 11 and 13. 11 is a polynomial, that should be easier. Let me do 13. It's harder. Natural log of x between 1 and 4. Okay, so how do you do that? All right, we know what the natural log function looks like. It's continuous everywhere. It's differentiable everywhere. Therefore, it's continuous on the closed interval from 1 to 4. And it's differentiable on the open interval from 1 to 4. Okay. It's a natural log. Logarithmic functions are continuous everywhere they're defined. Okay, so that satisfies the hypotheses. Remember, the hypotheses are the givens. That's what's given in a problem. All right, so let's find the slope of the line joining 1 and 4. So f of 4 minus f of 1 divided by 4 minus 1. That's y2 minus y1 divided by x2 minus x1. So natural log of 4 minus natural log of 1 divided by 4 minus 1. Natural log of 1 is 0. So ln 4 over 3. Okay, so somewhere between 1 and 4, the derivative is natural log of 4 over 3. And they're asking us to find where is that location. Okay, so where does that happen? So I take the derivative. Derivative ln x, 1 over x. Set it equal to natural log 4 over 3. Okay, flip both sides. If two things are equal, their reciprocals are equal. Does that make sense? So flip that, x, flip that, 3 over natural log of 4. Okay, so that's the C value. C is 3 over ln 4. And to just double check, is it between 1 and 4? I punch it on my calculator, it's about 2.16. Okay, and 2.16 is definitely between 1 and 4. Okay, so check that. 3 divided by ln 4, 3 divided by ln 4. 2.16, blah, 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 blah. Okay, notice it's not exactly in the middle. It doesn't have to be exactly in the middle, but just somewhere between the two. All right, so that's what's happening for that one. Okay, then 15. Find a number C that satisfies the conclusion of mean value theorem on the given interval. Okay, so f of x equals radical x from 0 to 4. Okay, so never mind about the graphing calculator icon part. So don't do that. Just go ahead and do what they're asking for. But I went ahead and graphed it anyway. Square root of x looks like that, right? Between 0 and 4. Plug in 0, 0. Plug in 4, 2. So 0, 0 to 4, 2. Square root function, continuous between 0 and 4. Yep. Differentiable between 0 and 4, not counting 0 and not counting 4. Yes, it is. The function is not differentiable right at 0. Okay. But everywhere in between. All right, so the slope is a half. Right, 2 minus nothing divided by 4 minus nothing, that's 2 over 4 or 1/2. Okay, so somewhere between 0 and 4, the slope is a half. And you're saying, find where that is. All right, so I take the derivative. derivative square root of x, remember that's like x to the 1/2. So 1/2 x to the negative 1/2, which is 1 over 2 radical x. Set it equal to 1/2. Okay, cross multiply, it basically means 2 radical x equals 2. So square root of x has to be 1, right? If square root of x is 1, then x is 1, or c is 1. Okay, so the ordered pair is 1, 1. So here it is. So the slope right here is 1/2, which matches the slope of the line joining the two endpoints. Again, notice it's not right in the middle. Exactly halfway between 0 and 4 is 2. We had a problem where it was exactly in the middle, but it doesn't have to be. It looks like it's in the beginning right here. Okay, so slope is 1/2 here, slope is 1/2 here. Again, think of it as Rowe's theorem tilted. If I turn it like that, okay, and you say the paper's slanted, but if you can just pretend you don't see the slant, it kind of looks like Rowe's theorem. Say, oh yeah, slope is 0, slope is 0. Right? All right, then 17 is the last one, then I'm finished. Then we'll get started with 4.3, which is a very big section. It's a deep section, a lot of good stuff in it. All right, f of x equals x minus 3 to the negative 2. Show that there's no value of c in 1, 4, such that f of 4 minus f of 1 is equal to f prime of c, 4 minus 1. The way they write that is, that alternate version that Mr. Stewart gave, but it's basically the same thing. Okay, so what do they mean? I seem to knock this out of focus a little bit. Looks like it's worse than before. Okay, I'm pretty sure you can't see that very well. So I go like this. All right, so x minus 3 to the negative 2 is the same as 1 over x minus 3 squared, right? And we're going from 1 to 4. Okay, so what's the slope of the line joining the two endpoints? So f of 1, plug in 1. 1 minus 3 is negative 2. Negative 2 squared is 4. So 1/4. F of 4 is equal to 1. Plug in 4. 4 minus 3 is 1. 1 squared is 1. 1. So my 2 points are 1, 1/4 and 4, 1. So find the slope. y2 minus y1 divided by x2 minus x1. 1 minus 1/4 divided by 4 minus 1. That's 3/4 divided by 3. 1/4. Okay, 3/4 divided by 3 means 3/4 times 1/3, and you get 4. Okay, but f prime of x, what is the derivative function? The derivative of x minus 3 to the negative 2 is negative 2 x minus 3 to the negative 3rd, which I can write like that. Set that equal to 1/4. Cross multiply, x minus 3 cubed equals negative 8. Take the cube root of both sides. X minus 3 is negative 2. X equals 1. Okay, 1 is not strictly speaking between 1 and 4. It's one of the endpoints. Okay, so in other words, there is no c strictly between 1 and 4, such that the derivative comes out to be 1/4. Okay, then the question asked, why does it not contradict the mean value theorem? Question 17. Why is there no contradiction? Okay, I think you can probably see why from here. The function is not continuous everywhere between 1 and 4. Function is not defined for 3. You're not allowed to plug in 3. Right, so f is not continuous at x equals 3, which means f is not continuous everywhere on a closed interval from 1 to 4. So that does not contradict. the mean value theorem. Okay. Right, so that's basically it for the mean value theorem. I'm gonna see if I can get back to where I was in focusing, but this might require some experimentation more than I want to do. But anyway, at least I can do this raising up. So let me give you the focus job for what we've done so far. And there we go. Okay. All right. So I'm done with the mean value theorem. Let me mark this off. Okay, so 4.2 is done, and I'm ready to start 4.3, which I wasn't supposed to start until Thursday, so we're a little bit ahead. Okay, so I'm done with 4.2, begin 4.3, which is a much bigger section. Let me try to go like this. And I don't see it as being any better, but be that as it may. Okay. All right, so 4.3. Almost all of 4.3 involves graphing. Okay, how derivatives affect the shape of a graph, page 293. Let me try to go like this. All right, so figure 1. Raise it up. Okay, Mitchell, can you see those little red tangent lines there? Oh. Okay, so here's a graph. We would say increasing, decreasing, increasing, using the language of roller coasters again, I suppose, or right. We're always going from left to right. So pretend you're on this roller coaster ride. Okay, or you say, I don't like roller coasters. You're driving or you're walking, always going from left to right. So increasing, decreasing, increasing, right? Maximum, minimum, slope is 0, right? All right, here the graph is increasing. I'm going up the roller coaster. I'm going down the roller coaster. I'm going up the roller coaster. Okay. What they're trying to show you with those red tangent lines is what's the slope over here? Positive. Think back to algebra 1. Slope positive means the line's going like that, right? Slope is 0 is like that. Slope negative means it's like that. Slope negative, slope negative. And then once again, positive. Okay, and I'll try to raise it up again. Okay, now can you see those red tangent lines, right? So between A and B, positive slope. Between B and C, negative slope. From C to D, positive slope. Okay, so between A and B, if you're on that roller coaster ride, you're kind of going like this, right? And then between B and C, you're going down. And then from C and D, you're going back up again. All right, so that leads you to this big GRU. Again, you can put it on your cheat sheet or not. Again, if we met face to face, I'd make you memorize it. I don't think it's that hard to memorize, frankly. Okay, increasing, decreasing. If f prime is greater than 0, f is increasing. F prime less than 0, f is decreasing. Okay. Translation, positive slope, negative slope. Okay, maybe I'll even put that here. M positive, M negative. Think back to your algebra 1, right? F prime means slope, slope positive. So algebra 1, slope positive. Oh yeah, it's going like that, increasing. B, F prime, i.e. slope, negative. M is negative. Oh yeah, algebra 1, it looks like that. That means I'm decreasing. Okay, so if the first derivative is positive, function's increasing. First derivative is negative, function's decreasing. Okay. Now, how can I tell if I have a maximum or minimum? Local extreme values. I'm on page 294 right now. So look down at figure 3, bottom of 294. Okay, it's a little bit out of focus, sorry. That's pretty bad, but anyway. Okay, take a look. Slope is 0, slope is 0, slope is 0, slope is 0, right? Raise it up. That looks like a local max. That looks like a local min. That's neither. That's neither, right? How can I tell if I have a local maximum? Well, take a look. If I move a little bit to the left, derivative is positive, increasing. If I move a little bit to the right, derivative is negative, decreasing. How about B, minimum? If I move a little bit to the left, function is decreasing, f prime is less than 0. If I move a little bit to the right, f prime is greater than 0, increasing. How about C and D? C, if I move a little bit to the left, it's increasing. A little bit to the right, still increasing. So that means you're neither at a maximum or minimum, right? That's not a maximum because you can still go higher. That's not a minimum because you can go lower. Likewise for D, it's neither. If I move a little bit to the left, function is decreasing. If I move a little bit to the right, function is still decreasing. So again, no maximum or minimum. So what's going to happen is we will take the first derivative, set it equal to 0, then say, how do I know if it's a maximum or minimum? If the graph goes from increasing to decreasing, you're at a maximum. If the graph goes from decreasing to increasing, minimum. Think of the roller coaster ride, right? You're on a roller coaster, you go like this. That means you maxed out. If the roller coaster ride goes like that and then like that, that's a minimum. What if the roller coaster ride goes like that? Increases, slope is 0, and then quickly goes back up. And I've seen roller coasters that do that, haven't you? You've maybe been on a ride that kind of goes like that, levels out, goes up. And so, well, that's neither a maximum nor a minimum. And likewise here, you go down, levels out, and then goes down again. If the roller coaster ride goes like that, again, this is neither a maximum nor a minimum. Okay. I've seen some slides, like playground slides, that look like this, right? It goes like that, then it levels up, and then it drops back down again. Okay. So that's how you can tell if you have a maximum or a minimum. Okay, so on page 294, they call this the first derivative test. And as you might guess, if they say first derivative test, there might be a second derivative test. Okay, so this, got that a little bit better. If f prime changes from positive to negative at C, f has a local maximum. That's part A. Positive, negative. B, f prime changes from negative to positive, then we have a local minimum. If f prime is positive to the left and right, or negative to the left and right, then we don't have either a relative maximum or minimum, right? That's this case, positive, positive. Well, if you go up and then you still go up, it's neither a maximum nor a minimum. And if you go down and you still go down, it's neither a maximum nor a minimum. Okay, you can put this on your cheat sheet if you want to. In my opinion, you don't really need to. Again, if we were meeting face to face, I'd make you memorize it. But after you do enough of these kind of problems, you kind of get the hang of it. Okay, so I think it's unnecessary to put this down if you do the homework. If you do the homework and you know what's going on, no need to write any of this stuff down. Okay. All right, new stuff. Something called concavity, page 296. Concavity. In case one doesn't have anything to do with your teeth, like cavity. Okay, concavity. So funny words. Concave upward, I'll normally just say concave up. Concave downward, I'll normally just say concave down. So we don't even know what it means yet, but I'll show you in just a second. So concave up, concave down. First thing I want to say is neither you nor I wants to write that whole thing, concave upward or concave up, concave downward, concave down. So can we come up with nice abbreviations? Concave up, CU. Concave down, CD. And the author uses that. CD, CU, C, concave down, concave up. Okay, so what is this concave down, concave up stuff? Right. If the graph is curving like the letter U, okay, imagine the letter U. Okay, it's curving the same way the letter U would. That's considered concave up. Okay, easy way to remember is U shape, concave up. Okay. If the graph is generally going in an upside down U fashion like that, that's considered concave down. Okay, so concave up, U shape. Now, you don't have to see the entire U, right? I mean, that kind of only looks like part of the U. It's still considered concave up. I guess if you turn the book like this, you can kind of see a little bit of a smiley face, right? Concave up. And concave down, you don't have to see the entire upside down U, okay, but just a portion of, or again, I guess if you turn it like that, you can kind of see the sad face, I guess, you know, smiley face, sad face, frowning mouth kind of thing. Okay, so that's concave down. It's the way it's curving, concave up, concave down. Okay. What's happening here is, first notice a characteristic. They're trying to draw you some tangent lines here and some tangent lines here. Okay. Now you can put this down on your cheat sheet or not. I don't think you have to, but it's just an observation. What's true about the tangent lines here, concave up? Tangent line, tangent line, tangent line. They seem to be below the graph. How about the tangent lines here? Above the graph. Okay. So that is true. If you have a concave up situation, tangent lines are below the graph. Concave down, tangent lines are above the graph. Okay, do you have to memorize that? I don't really think so. I mean, if worse comes to worse, if you had to do it, just draw yourself a U shape or upside down U shape, draw yourself some tangents, and then say, oh yeah, these are below and these are above, right? So no big deal. All right. What they're trying to show you here is concave down, upside down U shape, concave up, U shape, concave down, upside down U shape, concave up, U shape, concave up again, U shape, concave down, upside down U shape. Okay, so hopefully you can distinguish between concave down and concave up. Right. Now, so that's concavity. How can I tell if we have a concave up or concave down? Okay, let's look over here. So here are the tangent lines, see in red. So it's like that, and like that, and like that. So what's happening to the slopes? Slopes are increasing. What's happening to the slopes here? Decreasing. Okay, so the slopes are either increasing for concave up, decreasing for concave down. Now, we just got finished saying that if a function is increasing, its derivative is positive. If a function is decreasing, the derivative is negative, right? Slope can be thought of as a function. After all, f prime is a function, okay? So in this case, the m's are increasing. That means m prime is greater than 0. Okay. But what is m itself? M is f prime. So m prime can be thought of as f prime prime, f prime greater than 0. Okay. Likewise, here the m's are decreasing. M's are decreasing means from the rule we just saw, okay, that M prime is negative. But M itself is F prime. So F prime prime is negative. Now, if you understood what I just said, great. You say, I have absolutely no idea what you were saying. That's okay. Here's the result of what I talked about, whether you understood it or not. And this is what you want to do. And you can put this on your next cheat sheet if you want. Concavity is controlled by the second derivative. That's the key thing now. Okay. So if you understood this analysis that I said about the second derivative, great. If you don't get it, just be able to use the algorithm. Concavity is controlled by the second derivative. F double prime greater than 0 means concave up. F double prime less than 0, concave down. Okay. And I would abbreviate. If you're going to put this in your cheat sheet, CU, CD. Okay, double prime greater than 0, concave up. Double prime less than 0, concave down. Again, if we were meeting face to face, I'd make you memorize it. Okay, I'll go ahead and tell you the memory trick I would teach my class if you had to memorize it. Okay, positive is up, positive greater than 0, up. Well, just think of the y-axis, right? If you think of the y-axis, positive is up. So you have to guess, right? It's either going to be up or down. So positive is up, which means negative is down. Like the y-axis, it's down. So second derivative less than 0, concave down. All right, so first derivative controls increasing, decreasing. Page 293. Second derivative controls concavity. Right here. Second derivative positive, concave up. Second derivative negative, concave down. All right. Notice that does not cover all possible scenarios, right? What's not on this list? See, I got greater than 0. I got less than 0. What else is there? Equal to 0. What happens if I have equal to 0? That means it's neither concave up nor concave down. Page 297. Inflection point. Okay, inflection, not infection, inflection. An inflection point, by definition, the function is continuous, and the curve changes from concave up to concave down, or vice versa, at that particular point. Inflection point. Example. Inflection point changes from CD to CU. Inflection point changes from CU to CD. Inflection point changes from CD to CU. However, this point here is not an inflection point because it's concave up to the left, also concave up to the right. So it's not an inflection point. And that looks like an inflection point, change from CU to CD. Okay, inflection point. Here's a couple of examples of inflection points on a real graph. Okay, this looks like concave up or down. Can you tell? Looks like concave up. Then switch to concave down. That means this is an inflection point. And then after that, it looks like concave up. So another inflection point. Okay, so second derivative equal to 0, equals 0 might give you an inflection point. It's not a guarantee of an inflection point. It might give you an inflection point. Okay, you have to check to see, is the graph switching from concave up to concave down or vice versa? Because if it doesn't, then you don't, by definition, have an inflection point. Okay, we'll see all of this. All right. There is also a second derivative test for max and min. Again, you can put this on your next cheat sheet. I know there's a lot of material here, a lot of stuff going on. Okay, we already had a first derivative test for max and min, right? Max. increasing, decreasing. Min, decreasing, increasing. Neither, because increasing, increasing, decreasing, decreasing. Okay. There is a second derivative test. Let's take a look at this minimum point, right? That's a minimum. What's the concavity here? Is that concave up or concave down? Okay, which is which? U, the letter U, just think of the letter U for up, right? U shape. Is this U shape? Yes. Concave up. Minimum. Okay. What's the concavity here? Upside down U shape. Concave down. Maximum. So we actually have another test for maximum and minimum. We're going to be using both. Okay. So suppose f double prime is continuous near C. Okay. F prime of C is 0. Critical point. Critical point. Second derivative positive. Concave up. Minimum. Graph looks like that. Second derivative less than 0. Concave down. Maximum. Okay. So that's what we have. I know there's a lot of stuff, but we'll try to get you through all of these. Just generally what's going to happen is we're going to be able to graph neat stuff like this. We'll be able to find inflection points, maximum, minimum, stuff like that. Okay. All right, so last few remaining minutes, get started with something. Okay, not much, but a little bit. Okay, so what's our assignment? We've got this mixture of problems in 4.3. So let's see. 1, 2, so I'll do 2, you do 1, 9 to 21, 25 to 31, and then a mixture of other problems at the end. Okay, a lot of these are curve sketches. Let's look at number 2. Okay, and yeah. Okay, I see the focusing is a little bit better, but I need to move the arm up a little here. Okay, there's 1 and 2, and then 9 to 21 is way over here. Whoops, it went up on its own. 9, 17, 19, 21, 25 to 31. Make up your own graph. That has the following properties. Then what else? 37 to 53. Okay, so these are full-fledged curve sketches. And the directions for 49 to 56. Okay, and so as not to keep doing the same kind of thing, I'm going to be jumping around. We'll do some of each type of problem. All right, so maybe let's just start with number 2, and that might be all the time that we have. Again, sorry, I won't be able to write this. Big issue when you can't focus on this thing. Okay, number 2. Give the open intervals in which f is increasing. Okay, these are all open intervals, so you should write them with parentheses. So on this roller coaster, remember you're always going from left to right. Where are we going up? Okay, so between 0 and 1, so put parentheses 0, 1, union here to here. So where's that? Let's see, 1, 2, 3 through 5. So put union parentheses 3, 5, and then union 5, 7, I guess it is. 1, 2, 3, 4, 5, 6, 7. Right. Okay, so parentheses 0, 1, parentheses. Union 3, 5, all parentheses, union 5, 7. Okay, strictly speaking, right at 5, we're not increasing or decreasing. The slope is 0. Right, the roller coaster ride comes ever so slightly for a slope of 0, and then goes back up. Okay, B, decreasing. When are we going down the roller coaster? Only from here to here. So where's here to here? 1 to 3. So parentheses 1, 3 parentheses. Okay, concave up, U shape. U shape, upside down. Okay, it looks to me U shape from here to here. So that's going to be what? 2 to 4. So put parentheses 2, 4. Union here to here. So where's here to here? Was that 5 again? 1, 2, 3, 4. Right, 5, 7. Okay, so parentheses, all parentheses, 2, 4, union 5, 7. D, concave down, upside down U shape. So everywhere from here to here. So parentheses 0, 2, union here to here. So what's that? 4 to 5, union 4 to 5. Okay. People who design the roller coasters have to keep all of this in mind. And if you ride in a roller coaster, I know most of you don't think about this when you're riding an amusement park, you just want to go and have fun, but you see all of these things, right? Where's it going up? Where's it going down? Increasing, decreasing, concave down, concave up. People behind the scenes have to make the roller coaster design. Says, okay, now we're going to go up, but concave up and concave down and all that kind of stuff. All right, points of inflection. Inflection point, change of concavity right here. So where's here? 2, 2. So E is 2, 2. And let's see, that's another inflection point because that's concave up, that's concave down. So where's here as a point? 1, 2, 3, 4, 1, 2, 3. So 4, 3. And one more right here. 5, 4, isn't it? 1, 2, 3, 4, 5, 1, 2, 3, 4. 5, 4. Okay. All right, so that's pretty much it, folks. I'll just mention off to the side, inflection points are at certain points. For those of you that like roller coasters, you get that strange sensation, sort of. Okay, you know how in a roller coaster you go like that, and then it switches like that. You kind of feel that, whoa, feel like you're falling off, and it all of a sudden drives you back into the coaster. Likewise here, there's a certain sensation. You kind of go like that, and then it all of a sudden pushes you back upward. So you get that strange feeling. That happens at inflection points of roller coasters. Okay, not that I'm saying you have to think of all those things if you're on a ride. I think of those things on those rides, but you don't have to, obviously. So anyway, all right, so that's basically it for today, folks. So next time we'll do more problems involving 4.3. All right, that's it for today, folks. Everybody have a good day, and we'll see you next time. Okay, bye, everybody.
Bye.
Bye.